Okay, so we want to extend the notion of a sum of two vector spaces or subspaces and define something called a direct sum. And here's the motivation. I'm going to do a couple more examples of sums, and they're going to lead us to this definition. Let's recall what the definition of a sum is. So we have two subsets, and we're thinking of two subspaces. Their sum is just all the guys of the form something from U plus something from W. Okay, all sums of little guys. That's the sum of the spaces, okay? And the theorem we had that if we take two subspaces, then their sum is also a subspace. Not just a set, but a subspace. Okay, and we proved this. So here are two more examples. Two more examples of sums of subspaces. So so here's example 1. In all of them, V is going to be R3. In all of them. In both of them, V is going to be R3. That's the ambient space. And in example 1, W is going to be, I'm going to not write all the details, okay, in order to save time and space. W is going to be all the guys of the form 0, 0, C, where C is some scalar, okay, 0, 0, C. And U is going to be all the guys of the form A, B, 0. Okay, so geometrically, V is three-dimensional space, U is the xy plane, right? All the guys of the form A, B, 0. They don't have a z coordinate. It's the xy plane. And W is the z-axis. All the guys of the form 0, 0, C. It's just the z-axis. Do you agree? Okay. What is U plus W? U plus W is all elements of the form something here plus something here. So what is it going to be? Right, it's going to be everything. It's any element of the form. It could have any A, any B, because it's something here, plus something here, so it can have any C. So this is just V. Do you agree? Okay, so this is their sum, not their union, their sum. Okay, maybe let's write that this is R3. Okay, but I want to draw your attention to something that happens here. If you take a general element in R3, a general element is a vector of the form A, B, C, right? That's a general element in R3. There is only one unique way to write it as an element here. There's one unique way to take a general element in R3 and write it as an element here. You have to write it as AB0 plus 0, 0, C. There's no other way to write it as an element in this sum. Do you agree? If you take the vector 1, 2, 5, the only way it can originate as a vector in the sum is 1, 2, 0 plus 0, 0, 5. Do you see that? Okay, so any vector in R3 can be written as a vector in U plus W in a unique way. Do you agree? Here's example 2. I want to put it on the same board. Here's example 2. Let's take U is still going to be all the guys of the form AB0. And W is going to be different now. W is going to be all the guys of the form 0, C, D. Okay? So in U, we're allowing anything we want in the first two coordinates, and we're forcing 0 in the third one. In W, we want anything, we're allowing anything we want in the last two coordinates, but we're forcing 0 in the first one. Okay? First of all, do you agree that both of these are subspaces? Right? Geometrically, this is the xy plane, this is the yz plane. Do you agree? If you add two of these, you get something in this. If you multiply two of these, if you multiply one of these by a scalar, you again get something with a 0 in the first coordinate. They're subspaces. What is their sum? What is u plus w in this case?
A, B plus C, and D.
Okay, so in general, it's going to be adding somebody like this plus somebody like this, right? So it's going to be everything of the form A, where A can be anything, B plus C, where B and C can be anything, and D in the last coordinate. What is this thing?
V.
It's all a V. Any element in V can be written like this, right? For example, take C to always be 0. Do you agree that you obviously can never get something bigger than the ambient space, right? You can't suddenly have things that came out of your world, right? So this is just everything. This is, again, R3. Do you agree? Okay. But there's something different now. It's no longer true that any element in R3 can be written uniquely as something here plus something here. So, for example, if you take the element, so now, or not now, well, it's now, but the point is that in this example, so there is no longer a unique way to write elements. So namely, suppose you take, let's take a concrete example. Let's take 1, 2, 3. You can write it, for example, as 1, 2, 0. This is an element in U plus 0, 0, 3. This is an element in W. Do you agree? But you can write this as 1, 0, 0 plus 0, 2, 3. Do you agree? And again, this is a legitimate element in U, and this is a legitimate element in W. So you can write the same element in two different ways, and in fact, infinitely many ways, right? You can write it as 1, 1, 0 plus 0, 1, 3, right? And you can write it as 1, negative pi, 0, and 0, pi plus 2, 3. Okay, so there are infinitely many ways to write this element as something here plus something here. Okay, so in both cases, the sum of the two subspaces was the entire space in this case. The sum was the same in both two examples. Okay, but this one had a property that this one doesn't. Here we have a unique way of writing something as an element in the sum, whereas here we don't. Do you agree? Now think for a minute. Can you see another way of expressing the difference between these two examples? What enabled us to write this in two separate, distinct ways? There was another property of U and W here versus U and W here that allowed us to here, in this example, to write it in two separate ways and would not allow it here. Can you see that property?
The middle row, they have an overlap.
Right, they have an overlap. Very good. And our professional word for an overlap was an intersection. Here, these two spaces don't intersect. Well, right, they do intersect, but trivially. Their only intersection in example 1 is 0. Do you see that? And here, their intersection is not trivial, right? Their intersection is everything. The guys that are both in U and in W are all the guys of the form 0 something 0. Do you agree? 0 something 0 is an element here as well as an element here. So maybe let's write that. Let's take a different color. I don't want to use another board. I want to write it here. So In example 1, let's erase the title, giving us an extra line. And let's erase this. So in this example, U intersection W is not empty, but it's only the 0 vector. This is the only vector that's in both of them. Okay, so that's why you don't have any flexibility of moving things from one to the other when you want to write something as the sum of something here plus something there, right? Whereas here, the intersection, U intersection W, is all the guys of the form 0 something, let's call it E0, where E is anything, right? All guys of this form are both in U and in W. And this is what allows you to move things from one to the other. Do you agree? Okay. This is what we're going to call a direct sum. And this is what we're going to call a sum, but not a direct sum. Okay, that's the definition that's going to follow now. Is it clear? Is the difference between these two examples clear? Okay, so let's do it. Let's write what we claimed we're going to write. So definition, U plus W is called a direct sum. This is a broader notion from, you can even think of it as far up as category theory, and I'm not going to even tell you what it is. It's a notion that shows up in many, many fields of mathematics, and here we're only discussing it in the realm of subspaces of vector spaces. Okay, but it's a much broader notion. So U plus W is called a direct sum if any element in the sum, if any element in U plus W can be written uniquely as U plus W, where U is in U and W is in W. Okay? So that's the definition. Example 1 was a direct sum. So example 1 was a direct sum. Example 2 was not. Good? Okay. And the theorem is, which was our observation in blue in these previous two examples, that suppose U and W are subspaces of V, U and W and V subspaces, then U plus W is a direct sum. The sum is always defined, and we proved in the previous lesson that it's always a subspace. But it's a direct sum, namely any element can be written uniquely, if and only if, remember this notation, if and only if U intersection W is just a 0 element. So this is in fact a criteria. You can check this. If the only element in the intersection is 0, then the sum is a direct sum. Okay? It happened in the examples. It doesn't mean that it happens always. We need to prove this if we claim that this is a theorem. Good? So let's do that. Let's prove this. So proof. We need to prove two things, right? We need to prove two directions. We need to prove that if it's a direct sum, then the intersection is only 0. And then we need to prove separately that if the intersection is only 0, then it's a direct sum. That's what it means to have an if and only if statement, that you need to prove this implies this, and this implies this. It's two statements in one. So let's do it. So proof, I'm going to start by proving this direction. So I'm assuming that it's a direct sum. I want to show that the intersection is 0. So take an element, any element, V, in U intersection W. Take an element in the intersection. What do I want to prove?
There is only one way to write it.
No. It's this direction. I assume that it's a direct sum, so I'm assuming that there's only one way to write every element, and I want to prove that the intersection is 0. So what I'm going to do is here's V, here's U, here's W. I did the sum. It's hard to draw the sum, right? Usually the way I think of drawing a sum is in fact geometric. I take the x-axis and the y-axis, and the sum is the entire plane. Do you understand what I just did? Okay, I think of it geometrically. That's easier to describe rather than with these potatoes. That doesn't work here. Okay? So I'm taking a general element in the intersection. I want to prove that it's 0, necessarily. Okay? So take V in U intersection W. Let's write it. I can always write it as V plus 0. Do you agree that this is the same thing? Okay? Do you agree that I can just as well write it as 0 plus V? This I can always do. Okay? When you look at it, you may be thinking, wow, these are two different ways to write the same element, right? Here I wrote it as V in U plus 0 in W, and here I wrote it as 0 in U plus V in W, right? It's clearly an element of the intersection, okay? But the assumption is that there's only one way to write it as something in U plus something in W. That's the assumption. Do you agree? But if there's only one way to write it, then the U part in both ways has to be the same thing. Do you agree? So write this, and since there is a unique way, there is only one way to write V as U plus W, where U is in U and W is in W. That's the assumption of this direction. We're assuming it's a direct sum. Then the U parts have to be the same thing, and the W parts have to be the same thing. So we didn't just prove, we wanted to prove that V is 0. We didn't just prove that V is 0, we also proved that 0 is V. Do you agree? That's of course the same thing, but we proved it double. Okay, so V has to be 0, because the U portions of this decompositions have to be the same, because there's only one way to write it. And in fact, 0 has to be V. And since there is only, it follows that V was nothing other than 0. Clear? What I meant to say, Abba, you were supposed to laugh. Since you didn't, I'm assuming that you didn't understand my statement. We proved that V is 0 because the U parts are the same. But we also proved that 0 is V because the W parts are the same. So we proved the claim, double proved it. Okay, it's as convincing as can be. Clear? Good? Okay, at least you're laughing now. Okay, that's good. Okay, are we done?
No, we let it.
Right, we have to do the other direction. But is this clear? Okay, sometimes it's so easy that it gets confusing. Okay, everybody good? Okay, so now let's do the other direction. So the other direction, maybe let's take a new board. So now we're taking two spaces, two subspaces, U and W, and we're assuming that they have a trivial intersection. They're subspaces, so 0 is always going to be there, but we're assuming that nothing else is there. Okay, so now we're proving this direction. So let's write it so we don't get confused. Assume U intersection W is just a 0 vector. And let's prove that U plus W is a direct sum. Okay? I forgot to write the notation for a direct sum. Let's go back for a minute to the definition here. U plus W is called a direct sum if any element can be written uniquely, and now we're proving that this is another way of saying the same thing, but there's also notation, so let's write it down here. You can add it maybe right after the definition. Add it here. Notation. We write U plus W and add a circle around the plus. That's the standard notation for a direct sum. Okay, add this, please. Good? Okay, so we're back to the proof of this direction. We're assuming now that the intersection is trivial, and we want to prove that the sum is in fact a direct sum. Okay, so what do we want to prove? We want to prove that any element can be written uniquely. That's the definition of a direct sum. Okay, so take an element, V in U plus W. That's a general element in the sum. And let's show that it can be written in only one unique way as something from here plus something from here. Okay? Suppose you can write it in two different ways. Write it as U1 plus W1, and suppose you can also write it as U2 plus W2. Two different ways. If I prove that U1 is the same as U2 and W1 is the same as W2, then I'm done. That I proved that you tried to write it in two distinct ways, but you actually wrote the same thing twice. Okay, do you agree? Okay, so let's show that U1, so write this and prove and show that U1 equals U2 and W1 equals W2. Do you agree that this would complete the proof? Okay, so we know that V is U1 plus W1, and it's the same as U2 plus W2. So this means, so this is what we're going to do. So this means that I can subtract, right? Subtracting in a vector space just means adding the inverse, right? The additive inverse. So I can write U1 minus U2 equals W2 minus W1. Do you agree? I added minus U2 to both sides. U2 plus minus U2 is 0. This appeared here, and U1 minus U2 appeared here. And then I added minus W1 to both sides. Clear? So I'm doing this freely as if these were numbers, but they're not. They're vectors, but I'm doing legitimate stuff here. Clear? Is it clear why I'm pausing here to draw your attention to the fact that these are not numbers? These are vectors. Good? Okay. Now, where is this element? U1 minus U2. Where does it live? It's in U, right? It's two guys from U and minus U, right? And how do I know that minus U is in U?
It's the opposite one.
How do I know that it's in U? How do I know that if I took a vector, its additive inverse is there?
It's one of the subspaces.
It's a subspace, so we only checked that sums are there in...
It's a scalar. Alpha is minus 1.
Okay, so for example, it's a scalar product of U2 by minus 1, and it's a subspace, therefore it's there. Good? Do you understand that you have to be careful in these things? Okay, it really seems trivial to say these things if you're thinking in the world of numbers, but we're not. We're in the world of vector spaces. These can be, for example, two polynomials, or two continuous functions, or two 3x5 matrices. Okay, we're in an abstract vector space. So is it clear why this is in U? U1 is in U, that's how we started. U2 is in U, that's how we started. Minus U2 is in U, because it's minus 1 times U2. It's a scalar multiplication. And therefore there's sum. U1 plus minus U2 is in U. Good? Likewise, this is in W. Do you agree? So this dude here, which is an element in U, equals this dude here, which is an element in W. So it means that this thing is both in U and in W.
It's only the zero.
Right, but there's only one guy which is both in U and in W, which is 0. That's the assumption. So this, whether written like this or written like this, it's just 0. Because that's the only guy in the intersection. Since U intersection W is just 0. There's nobody else which is in both. Clear? So U1 minus U2 is 0. That implies that U1 is U2. And W2 minus W1 is 0. That implies that W1 is W2, which is what we wanted to prove. We took a general element in the sum, wrote it in two distinct ways, or seemingly distinct ways, and ended up with the fact that it was the same. Clear? And this completes the proof. Okay? I want to make a distinction. Again, this is not complicated. Okay? It's not that we somehow, pulled out of our hats a magic rabbit, or some, called to our aid some deep theorem from analysis or anything like that. This is, everything here is in an epsilon neighborhood of the definition. That's taken from calculus. Everything is just using the definitions. We didn't do anything complicated. It still may be confusing because you have to understand what you're doing. You have to understand the concepts and what you know, what you need to show, why everything follows. There's some careful understanding of the fact that we're working with vector spaces and everything is well defined here. Okay? So I'm not saying this is hard. I'm just saying read it again. Make sure that you understand what just happened. Okay? It's not hard. It's just it takes understanding to understand it. Okay? And you may need to read it again. Okay? Good? Everybody good? Okay. So you're going to see more examples of sums and direct sums and intersections and so on. But I'm going to stop our discussion of sums and direct sums here. And we're going to move on to the next topic, which we hinted to before. Suppose we just take a couple of vectors or a few vectors and want to form a subspace that necessarily includes those. Okay? That's what we call linear combinations, and that's our next topic.